Hello everyone. So today we are going to see the graphs, mainly graphs algo. So one of the important graph algo is MST. Does that you are given a graph. Let's take let's consider it as a graph. Okay. Now you are given weight. Weight to these is. Okay. So let's suppose weight is 2. It says 5, 6, 7, 9, 3, and okay. So convert it into tree, okay, or pick all the edges. You can say pick all edges, thus that each node are connected. Each node, all nodes are connected, not each, all nodes are connected, okay. And distance from any node to another node, yeah, distance from one node to another node is uh yeah, the path from one node to another node is should be always minimum. Like if I can go from here to here using 7, okay. No, instead I'm saying, yeah, we can go from here to here using 7, and using this we need 5 and 6, okay. One second. Given an undirected graph, a spanning tree of the graph G is a tree that spans G, that is, it includes every vertex of G and is a subgraph of G. Every edge in the tree belongs to G. Yeah, it should be connected. It is a spanning tree. What's the minimum? That the cost of the spanning tree is the sum of weights of all the edges. Okay, so we don't have to worry about between each of the node. Sum all of them, and it should be minimum, and it should be converted into a tree. Okay, such that all edges are connected. Okay, this is the problem statement. So how to choose the edges from this graph to make a MST, an MST. Okay, so yeah, this is the problem statement. There are two types of solution to this. Okay, I remember the name. The first one is Kruskal. The second is Prem's algo. Okay, actually I also know the algo. Okay, but still I'm gonna narrate it to you. So in Kruskal's, what we do? Okay, in Kruskal's, it is kind of a greedy algo, or what we can say, a greedy algo. So we greedily, at first we sort the whole array. Okay, we sort the no, array of edges. We create an edge list. Okay, edge list is taking all the edges inside it, such that let's suppose we are assigning it A, B, C, D, E, and F. So edge list will be AB, weight is 1. Okay, now AD and weight is 3, and dot dot, something like this. Now from all of this, okay, to okay, from this we have to create a NMST. Let me take, sorry, instead of it, let me take extra pages. So sidebar after, yeah. So let's try to, okay, so the Kruskal is, let's talk about Kruskal. Kruskal is to find an MST. Like suppose we have this. Okay, so what will be an MST? So whatever will be the MST, we know that this is gonna be part of it because it is the minimum edge. So this can be connected to this using 1. It is like damn sure, we are damn sure that it is gonna be part of it. What will be the next node that is gonna be part of it? This 2, because it is the smallest. What could be the next one? This 3, because this is again smallest. What could be the next one? This 5. Oh no, using this 5 it will become a cycle, it won't be a tree. Okay, there is a cycle. We can find A, B, C, and D as a cycle inside if we include 5. So we are not gonna include the 5. So what's next? 6. So let's include it. What's next? 7. Let's include it. Okay, no, no, we can't again include it too because it is gonna make a cycle. So let's not include it. After 7, what is again? Okay, so we have 9. So see, we have an MST now. This is same as Kruskal, okay? So Kruskal is taking all the uh, taking the minimum weighted edge in an iteration to create a tree, and that tree will be MST. This is Kruskal. Okay, so let's go through the documentation of HackerEarth. I will post this link in the in the description. Okay, so what is minimum spanning tree? It is saying the same. The cost of the spanning tree is the sum of weights of all the edges in the tree. There can be many spanning trees. Minimum spanning tree is a spanning tree where the cost is minimum among all the spanning trees. Okay, so it's done. Now about Kruskal. So let's see the step. Plot the graph of edges. Okay, instead of algo, we see Kruskal algo build spanning tree. Okay, it builds a spanning tree by adding edges one by one. Yeah, the same way we are adding edges. Like first we took okay, first we took this one AB, then we took BC, then we took AD, then we found okay, we can't take this because it will violate our property of tree because it contains cycle. Okay, so into a growing spanning tree, Kruskal algorithm follows greedy approach. As in each iteration, it finds an edge which has least weight and add it to the growing spanning tree. Okay, this is same. To prove it, like it is a greedy algo, so to prove it, okay, it is a bit intuitive too, but its proof is done like something like this. You are at ith step, you have to choose the next edge. So what is the edge you are going to choose? Something like this you have to prove. Okay, I don't remember it, but you can go through the proof. But in an intuitive way you will find it. Okay, if we have this, if we have the whole nodes, okay, we have A, B, C, D and everything. So what's the best option for us to choose? Of course this one. Okay, so we will choose this one. And given A be connected to it, what is the next best option? This too. So let's choose this. So you don't have to remember the whole proof. You can simply intuitively find this. Okay. And these weights are not negative too. Like, yeah, for this purpose, I don't think so. But okay. So what are we doing here? We are going through each edge, okay, and we are going through vertex to each vertex. So it would be order of v plus e, but before that we have to sort it also. So it will be like order of v log n, v log v, v log v plus v plus e, I guess. Yeah, we are also traversing all the edges, so something like this will be our time complexity. Let's see. So it is taking just order of v plus e. Yeah, it will be fine, but okay. Oh, it is about talking about DFS. Okay, whatever. So, so to implement Kruskal, yeah, this is the whole functioning. You can see. So there's one more concept which helps us in implementing Kruskal. We are gonna talk about it. Okay. So that concept is okay. So before that concept, let's check how we are going to implement the whole algo. So let's try to find an algo to solve this question. So what we have, initially we are given a graph. Okay, it could be a list of list, the such that, yeah, it could be a list of list, which is also known as what you can say. uh, okay, I don't remember. The next one is matrix. It could be given in matrix, or it could be having default list of list. Okay, the fourth one could be okay, edge list. If this is the case, our solution is like simple. We don't have, okay, this won't be in order of v log v, it will be order of e log e. We have to sort the edges now. So where's the gray order of e log e? Let me clear it. order of E log E. Okay, remove it. So final order should be like this. We have to check it, but according to me, it should be this if we are going to sort the whole array. And further, we have to access it, like check whether it is cycle or not. We are gonna do it in less than order of E log E somehow. Let's see how will we do it. Okay, so we have our edge list or matrix or something. Anything we are gonna convert into edge list. Okay, suppose in here we have AB as 1. This is our edge list. AB as 1 with weight 1. The next is BC. The next is that BC. The next edge ED. Okay, let's AB BC is 2, CD is 5. Okay, BC is 2, CD is 5. The next is AD is 3, something like this. We are gonna have AD is 3. Now we are gonna sort out this array on the basis of this weight. Okay, so this will come here, this will interchange because 3 is less than 5. Now what we gonna do, we will add AB1. Okay, we will take AB1. Next we will take BC2. Okay, then we will take AD3. So and the next when we go to CD5, then C and D should represent that it is already a component of the tree we have taken. Okay, so let us suppose take another example to understand it. This is 1, this is instead of 1 2, this is A, this is B, this is 1. Okay, this is C and this is D, and this is 2 and this is 1. Okay, and let's suppose we have one more edge, like this is 30, this is 35. So when we start our MSD, the Kruskal, we will found that the first answer will be this AB. Okay, the second will be this CD, but these both are not connected. Okay, the next will be these BC. Okay, now they are connected, and then we will check for these both of them. So we found that okay, there is a 30 in here. Then we will check for 35 and it will show us that it is creating cycle. So how could we found that two nodes when connected will create cycle? So to solve this problem, there is a concept called union find. Okay, it is like putting all the nodes, like putting this and this and this inside a set. Okay, let's make a set. Like when we, let's go back, when we did this, we are gonna create A and B set, the sorry, like this, A and B, because they both are part of one set. The another will be C and D. Okay, when we merge them, then we are gonna merge A, B and C, D. So its complexity, if we directly try to merge them, its complexity will go very high, like order of V for each iteration. So we need something else to make it work. So what we can do is, okay, we will use union find. So what is union find? In an efficient way, we are gonna make union of AB and CD. Okay, and to check, like, and then when we are doing BC, we have done BC. Now after that we will do something like I mean this with this one, and then when we are trying to do this connect to, when we will try to connect this E and D, we will find that okay, E and D both belongs to a single set. Okay, so we will find E, we will find D, we will say okay, both belong to same one, same set. So this is a whole concept. Let's try to implement it. So what we will do, okay, we have an edge list. Let's suppose this is our edge list. So for, and it is sorted. Okay, edge list are sort where key is equal to lambda. Okay, and x is x of 2. It will sort according to weight. Okay, now after sorting, so for each edge in edge list, for each edge in edge list, what we can do is our first node will be edge 0, the second will be edge 1. Okay, we are gonna find parent of edge 0 and parent of edge 1. So okay, we will take a parent 1. It will return find edge 0. Okay, same we will do with parent of 2, find edge 1. Okay, so if parent of 1 is equal to parent of 2, okay, just continue, we can't merge them. Else else make parent of 2 is equal to parent of 1. Yeah, this will work. So parent of 1 will become parent of 2. Okay, before, no, not like this. Then we will union it. Let's union, uh okay, union parent 1 and parent 2. Okay, but what if we won't find this parent 1? What if parent 1 is null? Then directly union it, okay, and consider it. And our MST will be appended accordingly, like when we are doing union, append it. So now how we union it and find it, that's the main issue. Okay, so to union and find, so let's suppose uh, we have a, so okay, we also need parent. Whenever we are doing union, we need parent or something like this. Okay. um so we can do here, what to do now? Okay, we'll find something. Let's write code to find it. To union, it will be depend upon code. It will depend upon code. So let's write the code. The video is going to be long, and I don't think that anyone gonna watch it because it's lame. Map int comma input dot split. Yeah, so we have our n, and instead of n, let's represent it as edge. Okay. What is second one is edge. The first one is 4. What is 4? The n represent vertices. So let's suppose this is vertices. The second one is edges. Okay. Now for I in range, or instead of I, let's use edge. For edge, yeah, for edge in range edges. Okay, let's create our edge list. Edge list equals empty. Now edge list dot append, yeah, let's directly take 1 2 and 4 7 inside it. So list of map of int comma input dot is, this will serve the purpose. It is a list, and I'm gonna append it inside edge list. Now what we will do, we are gonna sort the edge list dot sort is equal to lambda, and so x will be the sort according to the third index because that's the weight. Sorry. Now what we will do? Okay. Oh, we reached. Okay, so if we need to find parent, not parent. Okay, so like what we can do is we can traverse our edge list. We are gonna traverse our edge list somehow at the end. So for edge in edge list, our first node is edge 0. So instead of edge, we can say for uh what AB edge 1 edge 2 or edge A edge B. For edge 1 edge 2 EDG, okay, EDG. So edge 1 edge 2. Okay. So what we will do now, we will try to find parent of edge 1. Okay, parent is equal to find parent, or let's say parent of edge 1. The same we will try to do with parent of edge 2. Okay, parent of 1, parent of 2, edge 2. We got both parents. If parent 1 is equal to parent 2, then continue. Okay, if not parent, if not parent 1, or what we should use? Yeah, we can use it. Okay. No, parent 1 will return the node itself if it has no parent. Okay, we can do this. So like, what is parent in here? Let's define it also. So define parent. Okay, we are gonna pass a root inside it now, or a node. Let's suppose we are passing a node, and we are not creating any. No, yeah, we are not creating any. Okay, so parent node. So if if what? Let's create an array which will contain our parents. Yeah, initially parent for all of them is parent is equal to the vertex are 4. So if vertex 4 vertices are there, then it will be from 1 to 4. Okay, so I for I in range n, yeah, something like this, or n plus 1, let's say. Sorry, why are we using n? It will be vertices from 1 plus 1. Okay, this is our parent. So okay, now parent of node will be like return parent of node. Okay, so we don't need to use this function also. We can directly simply use this parent of h1, parent of h2. Yeah, so let's use this directly. We get both of their parents. So if both of their parents, so what does parent represent? Parent is like, instead of parent we can say the ancestor. Yeah, instead of parent we are gonna say its ancestor. So it will be like, let's take an example. So if we have two connected components, suppose this is first. Okay, the second is this. This is in order of like, first this come, then this has come. Okay, first this node has come, then this. I mean, first this edge has come, then this edge has come. Okay, then this. So it is in, okay, yeah. So each of them, each of their node will have parent. Okay, so this has a parent itself. This has again this as parent. So instead of parent, we can use word ancestor also. So let's stick with ancestor. It looks cool. Okay. Ancestor parent 1, ancestor edge 1, ancestor edge 2. Okay, so we have our ancestor edge 1 and ancestor edge 2. Now what we will do? If both are equal, yeah, if both are equal, then continue. We don't need to, okay. So that means both belong to same connected component and we don't need to append them. Okay, we don't need to add both of them because it is gonna create cycle. Adding, including them will create cycle. Something like this. Including them will create cycle. Yeah. So, and if it is not the case, then okay, then what we'll do? We will find yeah, so it is not always gonna represent ancestor. Yeah. So instead, what we will do, we will union it. Union parent 1 comma parent 2. Okay, we have to think how to union it. Okay, yeah, this is the code. Let's try to write our ancestor or ancestor of this and ancestor of this, and while so union means making both ancestors same, making both point to same ancestor, something like this. Okay, let's try to do this. This will be in order of what? I don't know. For each of whenever I'm in like checking, it will at first it will be order of n, but if we are checking for it again, like for same ancestor, then it will become order of 1, something like that. There is also a way to convert it into balanced tree. Check it out. Like we can for now we are gonna complete it first. So ancestor. Okay. No, this won't work. This won't work. Okay. We have to find this edge 1. That's why there's a function called find. Okay. Find the parent of edge 1. The same we are gonna do. Find the parent or ancestor. Like find the ancestor of edge 2. Okay. Find both of their ancestor and then do this. So let's remove all the ancestor thing. We are gonna use parent. Define find. So we will be given a node. So if parent of node, yeah, okay. Let's try to take an example to deal with it. Let's take this example. Okay. So there are like 1, 2, this is 7, 1, 4, this is 6. Now 4, 2, this is 9. Now 4 and 3 and 2 and 3. Okay. 4 and 3, this is 8. Now 2 and 3, this is 6. Okay. So when we started, we will union both of them. So initially, our parent array is this is 0. We don't have to use it. 1, 2, 3, and 4. Okay. When we union 1 and 4, we will convert our 4 into 1. Okay. So this is now current parent. So this is the scenario is like this. Let's take another color. So current. Okay. So current scenario is that we have taken 1 and 4. Next we take 2 and 3. Okay, let's take 2 and 3. So now this, convert this into 2. Okay, now the next edge, this 1 and 2. So for 1, check its parent 1. For 2, check its parent. This is 2. Both parents are not same, then like merge them. And now make the parent of 2. Yeah, make the parent of this 2 3, this is 2, point to 1. Okay, or you can do otherwise also, but let's do this. So yeah, this is the way we are going through. For each node we are converting its parent to someone else which is previously like here. Okay, so for 4 we have already, we have converted into 1. So if 4 is not like the 4, this, the here the value is now 1, 1 is not equal to index, its index, then go to the value which you found here. Okay, this is the way we are going to find the real parent of this whole, like it will be finding the root of it. Okay, so if parent of node is not equal to node, or what, yeah, parent of node is not equal to, we have to find it for node. If its parent is not equal to node, then instead of using if, use while parent of node is not equal to node, then parent of, make parent of node is equal to node, or sorry, node is equal to parent of node, node is equal to parent of node, and at the end return the real parent, return node. Okay, now it will work. So through this way we have found the real parent of this, or root of this connected component. And if they both are same, continue, else union. So let's define our union. Define union. So union will take two nodes. Okay, the first one will be, let's suppose A, then another is B. Okay, so what it could do, make it, okay, so union is like, let's check it. So this is pointing to something else, this is pointing to something else, we have to make point this one to this value. Yeah, this will work, like point any one of them to another one. So if we say like parent of A, make parent of A is equal to parent of B, yeah, then it will, yeah, this will be okay. So let's try to run it and check where is the problem, because I'm feeling like it is not that okay. Yeah, so if parent 1 is equal to parent 2, then continue, else union both of them, and here will be our result. So what we have to print, the MST length. Okay, so MST weight, something like this, is equal to initially 0. So if we are unioning it, I mean if we are taking union h1 h2 comma weight, then sum it, like MST weight plus equal to the weight of the current edge. Okay, now print MST weight. But union is like, if okay, it should work. Another thing is it will return node. Okay, everything looks fine. While parent of node is not equal to node. Okay, then go inside it and convert the node here. Let's compile it. Yeah, it is. Oh, yeah, it is passing. I have done this before. So last time what I did was while parent, yeah, I did same this time again. So okay, no, parent of this is equal to find parent and make it. Okay, this is working on in fine, but when I will submit it on another, it won't work because I have done a very like huge mistake. I have to make parent of node 1 is equal to uh before that we have to find the parent of node 2 and then assign it to node 1, parent of node 1. Okay, it won't work. So this was a wrong solution. Like it was wrong because here it TLE because if both are not, if parent of node is not equal to node, then make it like this TLE. So this is not a good value, I guess. So if parent of node and node are not equal, then node will become parent of node. Node will become parent of node. Yeah, it's okay. Then they will be both equal, then return node. Okay, before that let's find B. So find will return our node. It is passing the test case, but it is not passing the rest of it. What what could go wrong? Let's see. I have appended everything, sorted according to defined parent. While parent node is not equal to node, then make it like this. Union it, like parent of node 1 will be find another one and make it like this. Okay. PLE. Oh, I understood it. So if, yeah, this is the case. Like, let me show you one thing more. It must have also not passed because, yeah, if count is equal to this, then break. This I have to add. Yeah, that's what I thought. Because a tree can have maximum vertices minus one edges. Okay, so we are gonna count it. So count is equal to initially 0. And after this, count plus equal to 1. Okay, so if count is equal to n minus 1, sorry, vertices minus 1, then break. Okay, break here, and then, yeah, it will work. So let's see now. It's already 38 minutes. But yeah, now I'm confident in Kruskal and you will be too. Just okay, let's see the submission. Um, the main important thing is you have to make parent of A is equal to find parent of B, then convert it to it like this. Okay, it's got accepted. So thank you guys. We'll meet you soon with the next algo, which is Prim's algo. Okay, I'm gonna make it in another 5 or 10 minutes. Okay, bye. Thank you. Subscribe for more question. Meet you soon. Bye.